Alright, so this is it, the final event of the day and of the workshop, and the most special one. We've kind of grouped everyone together into their separate categories, but this is the time to bring them all together. This is the panel discussion for all possible signs of the cosmological constant. And for this very special panel discussion, Tarek has been willing to lead, and he has invited Eliot, João, and Loga, who have all been kindly willing to act as panelists. So I hand over the word to Tarek.
All right, so I want to, first of all, thank the organizers personally, Gideon, Kostas, Gizem, Joris, Andre. All thank you so much for organizing this wonderful workshop that has brought together a group of people that doesn't usually communicate with each other. And I think that's a really important thing, especially nowadays. And I think it's great to have a good perspective, like a broad perspective on all of these ideas. And so the topic of this workshop is really great. So since this is a panel discussion, let me see, why is this not working? Since this is a panel discussion on all signs of lambda, let's just kind of recap some of the questions that arose over the course of the workshop. So we saw in negative cosmological constant, there are some confusions. That's the state of affairs where we have the most control, the most understanding. But there are still some underlying questions. For example, is holography and ADS dual to a single quantum system, or is it dual to something more complicated like some disorder average theory or multiple copies of different conformal field theories? And a related question to that is, what are Euclidean wormholes, or what is Euclidean gravity in general telling us in the case of negative cosmological constant? For flat space, we have been mainly talking about what is the organization of the flat space S matrix, what kind of information is being carried off at infinity, and what is the structure telling us about the underlying theory? Can we learn something about holography in the case of lambda equals 0 from this structure that we seem to be uncovering, this very, very distinct stuff that just seems to live all the way up to the null boundary? And for positive cosmological constant, we heard a lot about the observables that are encoded in the wave function, but there are still big question marks about that. Are they appropriate? For example, when you include quantum gravity, when you integrate over the spatial metrics at future infinity, what good are these observables at the end of the day? And moreover, what does the Euclidean sphere tell us about de Sitter space? De Sitter space is the analytic continuation of the sphere. So what is known? So that's kind of, those are the broad themes that we heard all week. So I think in order to get a discussion going, I'm going to try to rile people up a little bit, ask people some questions that may be controversial, but I want to say the following. This may or may not be controversial to people in the audience. Holography is at its most powerful when we're able to say or extract something precise from it. For example, what is the exact value of some correlation function and how that's encoded in the bulk. So an alternative way to look at that statement is that holography is a machine that produces answers that we like. It's a machine that tells us, without us having to use this thing that we don't understand, which is gravity, it tells us the answer that we're looking for. For example, a correlation function n equals to 4 super Yang-Mills tells us something about interactions in quantum gravity, in ADS. So what does that imply? What does that imply for example, in the negative cosmological constant case? Well, we have a factorization puzzle, but that factorization puzzle comes from the bulk. It's a confusion that we have in the bulk. It's not that we have a machine that gives us an answer that we trust, where we can make, where we can say, ah, this is something confusing. So instead of calling it a factorization puzzle, I'd like to propose that it's more like a factorization choice. You can choose your machine to be some disorder average theory, and then you'll end up with something that doesn't factorize. Or if you choose your dual to be something different, like a single CFT, not a disorder average theory, some regular quantum system, then you get something that factorizes. And I think this corresponds in the bulk to a choice of measure. Do you or do you not include these Euclidean saddles, and with what weighting? This is a non-perturbative question from the gravity side that we don't really have access to unless you give us something bigger, some more omnipotent structure like a dual. So I think in order to really deconfuse ourselves about this, we need a better machine. We need better guidance. So that's my 2 cents on the negative lambda side. On the positive lambda side, we had a whole discussion panel just now, so I don't need to reiterate what was said, but I think an important point is that we need to understand how we can take all of this beautiful organizing principle that we're discovering about the asymptotics of flat space and build it in something more fundamental, like something like a machine that can give us answers. Maybe it's a matrix model, maybe it's a quantum field theory, maybe it's something else. But what we have currently is we have an answer that we want to reproduce, but we don't have a machine that gives it to us. And I think that perhaps something that we should talk about is how to build that machine. What should we do? Finally, we get to the last sign of lambda, the one that I think is most relevant to us, which is positive cosmological constant. Now, a lot of discussion was made, I mentioned this earlier, over the fact that what the bulk spacetime seems to produce is inflationary observables. This is relevant to, for example, the CMB. And those are observables that are pushed all the way to the time-like boundary of de Sitter. And then you can imagine exiting inflation, exiting the de Sitter, and then having access to the correlation functions on this slice. But what that really neglects is that you should still integrate over the graviton or the spatial metrics here. So when we observe the sky, what we see is we see well-defined observables for scalar fields of the inflaton. And that suggests that to a very good approximation, gravity on that slice is fixed and the metric doesn't fluctuate very much. And how do we produce that? What kind of models do we have that can really reproduce that in a self-consistent way that we say is quantum gravity rather than quantum field theory in de Sitter space? And a related question to that is, would these models have anything to say about the static patch? For example, the universe that our universe is asymptoting to, and our future selves will have to deal with. What is the physics of a single static patch? And finally, if you really think about quantum gravity and de Sitter space in a fundamental way, when you integrate over metrics or you consider the Euclidean gravity path integral, the Euclidean gravity path integral is a compact manifold, and so it would seem like there are no observables that you could even compute. There's no such thing as a local correlation function. What does it mean to insert an operator? So it seems like all you can get is a single number out of this object. What is that? How do we reconcile that with our lived experience of living on a world line? I think all of these are important questions. So with that, I hope to have given a broad overview of the big questions that I think were raised over the course of the week. And I think if any of these questions piqued your interest, then save them, because now we're going to go and give it away to our remaining panelists. So I think we should go alphabetically. So Eliot, would you like to go next?
Sure, I'll share screens if you allow me to.
I don't think I have the power to give you.
No, it's fine. I got it. Do you guys see my screen now? Do you guys see my screen?
Yes.
All right. Okay. So I'm going to be completely honest from the beginning. I barely understand ADS-CFT, let alone flat space holography, or whatever we mean with de Sitter holography. So in what I'm about to say, I'm going to keep it extremely simple and basic. I'm actually not going to talk about de Sitter space at all. I'm just going to talk about flat space. And I'm actually going to talk about flat space from the perspective of a flat limit of ADS-CFT. And to be clear from the beginning, I'm not going to say anything extremely deep. I'm just going to present some tools that I believe are useful to study quantum field theory in flat space from a holographic perspective using ADS-CFT. So the flat limit of ADS-CFT is a very obvious limit to study. It was studied already immediately after ADS-CFT by Polchinski in this very famous paper, in which he considered this large N gauge theory that was dual to type 2B, and then took a limit in which the ADS radius went to infinity. And then he studied kinematically what happens to the bulk, and he understood that the flat space should emerge, at least kinematically. And so anyway, this is a very, very intuitive thing to do. Sorry, I don't know why. Do you guys see the full screen, or is it cutting now?
When the panel, the thumbnails come up, it kind of cuts.
Yeah, sorry, I didn't know how to get rid of them, but they're gone now, right?
Yeah, no, they're gone.
All right, so I think one of the important things to talk about is the observables. Now, in gravity, it's difficult to define observables because we have diffeomorphism invariance, and in ADS-CFT, it becomes extremely simple because we have a boundary. And then in the boundary, we can place the conformal operators and then assemble correlation functions and study these kind of observables, whose main ingredient really are the state of the conformal field theory and the operators I use to assemble the correlator. Now, in flat space, we don't really have a boundary, right? I mean, we usually write this kind of no boundary and this Fisher infinity, past infinity, but there's not really a boundary, right? Things leaking through. And so it's difficult to define this kind of correlators like this precisely. The only precise observable that we think we have is the S matrix, right? In which we compute the overlap between different scattering states, and scattering states are defined in some past and some future Cauchy slices. So what I would like to understand is, if we're taking a flat limit, we should understand very well how these scattering states come from conformal operators in CFT. Now, there's many frameworks to study this. There's a lot of literature, and I have added no references in this kind of little presentation. There is an approach that uses the momentum representation of the CFT. For example, one is able to obtain graviton and gluon S matrices from stress tensor CFT correlators in momentum space. Another approach that is very interesting is understanding Mellin amplitudes as some sort of S matrix. This comes from the kind of nice properties of the Mellin amplitude that seems to be cross and symmetric and meromorphic, simple pole, so it makes it look like it's some kind of S matrix. And so indeed you can obtain several results for S matrix for masses and massive particles. And then there is the position space approach in which one tries to actually use position space operators in a CFT, smear them in some way, and construct the scattering states that one can use then to assemble an S matrix in the flat limit. And this third framework is the one that I have personally been working on, and the one that I'm going to explain, and that I believe provides with some tools that are interesting to study this flat limit. So in a couple of pictures here, the idea is very simple. So in this circle here that has this hyperbolic tiling, we can think of it as the anti-de Sitter space-time geometry. And somewhere deep into the center of ADS, we can think of being a physicist that has no access to physics beyond the ADS length scale. And so this physicist will see the geometry as flat. And so from his perspective, the tiling will just be flat. Now, if we look at the observables that one can compute, so in the bottom here, I have drawn the statement of the ADS CFT conjecture. It just tells us that the expectation value of some CFT object is given by a bulk path integral. And an extremely similar formula exists for the S matrix, right? In terms of a path, you can write the S matrix in flat space as a path integral over the fields in the quote-unquote bulk. And so the formulas look so similar. They're basically the same formula. So the only thing we need to figure out is how scattering states in flat space map to scattering states in ADS CFT. Or in other words, how do we take flat limits of a scattering state in ADS such that it becomes a desired scattering state in flat space? So what the tools that I think are useful to do this are, we know we can use them in ADS. We know them. I think the tool that we should use is bulk operator reconstruction. So in the case of free fields, we could use, for example, HKLL. And the idea is very simple. So if we have some scattering region somewhere deep into the center of ADS, and we think of the incoming fields phi as phi in and the outgoing fields as phi out, we think of those as local bulk operators. Then we can try to reconstruct these local bulk operators in the boundary CFT, then extract from them some modes like the creation and annihilation operators through a Fourier transform. And then after we're done with that, take a flat limit, some large radius of ADS limit. And that will tell us, just by first principles, what the map between creation and annihilation operators in Minkowski space is with conformal operators in the boundary of ADS. Now, something that I think is actually very interesting is that here, in this kind of when we reconstruct the operator, we need to decide what kind of dynamics the operator has in order to be able to reconstruct it in the boundary of ADS. And this basically, in the language of flat space, this corresponds to choosing some kind of asymptotic Hamiltonian. If we consider free fields, then that corresponds to this free asymptotic Hamiltonian. So this is the assumption of asymptotic decoupling in S matrix theory, and this leads to a Fock space. And so if we assume free fields, we should recover S matrix in a Fock space, and these S matrices will be IR divergent, etc., etc. So I think it's interesting to generalize this to more complicated asymptotic Hamiltonians. In any case, the result that you get from doing this mathematical operation, I think is kind of interesting. So let me explain first what happens to massless fields. So in these formulas that I have written here are the creation and annihilation operators for incoming and outgoing fields in terms of CFT operators. And as you can see, for example, for an outgoing creation operator, we have some overall constant, then some smearing over global time, and then the conformal operator. And the smearing over time is interesting because it's a large phase. This L here is the ADS radius that is going to infinity. And so this integral is actually going to be dominated by regimes of global time in which tau minus pi over 2 is small, which means that the global time is pi over 2 plus some windows of size 1 over L. So in this picture, this red fringe here is where we would have to insert a conformal operator such that that corresponds to an outgoing massless scattering state. And this makes sense because if in the center of ADS we have this kind of wavy massless particle, the scattering away from the scattering region, it will hit the boundary at around pi over 2. So it makes sense that inserting an operator somewhere there creates a scattering state in flat space. Now, for massive states, the situation is a bit more complicated because there's this mapping to the conformal dimension of an operator and the mass of an ADS field. And so the conformal dimension of the operator is actually going to scale with the ADS radius. We're going to have a heavy field. And the math of the problem is a bit different, and you get a different answer, but the result looks very similar. It's again some overall constant, then some very large phase, and the CFT operator. But now this overall phase only vanishes when the global time is pi over 2, but also some imaginary piece. which means that we are, instead of being in this red fringe, we're actually analytically continued into the bulk, basically along the Euclidean direction. And this introduces this kind of domes here, these Euclidean domes. And so this kind of picture makes it look like, if we want to consider some flat limit of ADS CFT, there seems to be two regions of our CFT that play an important role. One of them is the regions around pi over 2 and minus pi over 2 that play the role of null infinity. And the other regions is this kind of Euclidean domes that play the role of future and past infinity. In terms of propagation of particles, it kind of makes sense. As I said before, massless particles propagates around light-like geodesics. Those hit pi over 2. Massive particles follow time-like geodesics. Those never hit the boundary, which in other words mean that they hit the boundary at an imaginary point. Now, these results are for scalar fields, but you can use these tools to reconstruct whatever you want, gravitons, photons, whatever you want. For example, for photons, there are similar results. Now, instead of the conformal operator, you have the conserved current appearing in these formulas. But anyway, this is just a simple generalization. And something kind of interesting is that using this map between creation and annihilation operators in Minkowski space and CFT operators, you can actually show that the symmetries of the S matrix that for example, super translation symmetry or super rotation symmetry and all of this kind of interesting symmetries, that all of this BMS symmetry actually arises from a flat limit of the conformal word identities in a three-dimensional CFT. And so I think that's kind of an interesting take of what this BMS symmetry comes from. Okay, so just to finish, some stuff that I find interesting that could be analyzed using this kind of tools and this kind of framework is IR finiteness. So as I said, in this kind of formulas that I have shown you, I have assumed that the fields were free, which means that I'm assuming asymptotic decoupling. I think it would be interesting to understand what happens if the Hamiltonian includes the soft modes of our gauge field that should resolve all this soft theorem stuff and all these IR divergences. But this requires work on I think one way to go would be to try to understand this recent work on soft collinear effective theory in flat space, to try to generalize that to ADS and take a flat limit of that. Then another point that I think is interesting is to try to understand how the BMS4 charges explicitly arise from some object in the CFT, probably constructed out of the CFT3 stress tensor. But for the case of non-leaky ADS, so we saw some interesting talk by Romain yesterday, in which he talked about how to get BMS4 from a flat limit of leaky ADS. But I think it should also be possible to obtain such symmetries from non-leaky ADS. And of course, another interesting thing related to other talks that we have seen throughout this week is how all of this is related to the celestial sphere story. Here it's clear that we need a third dimension, right? I mean, this Euclidean dome requires this kind of Euclidean direction to understand massive particles. There's only 2 dimensions, so it's not clear to me how to dimensionally reduce this CFT3, but I think it's a kind of an interesting question. So yeah, this is all I wanted to mention for now.
Okay. Yeah, let's go on to João, and then we can have a broad discussion at the end.
Okay. Can you see my screen?
Yes.
Okay, thank you very much. So yeah, I think what I have to say, it's a bit simpler. So I think that even I will mostly speak about a context without gravity. I'll just make a few simple comments about gravity, because I think just quantum field theory in these backgrounds is already complicated enough. I think we still need to understand quantum field theory. So let me start. So I will go in increasing order of complexity. So it's also growing lambda. So for negative lambda, I think the situation is quite good. So for quantum field theory in anti-de Sitter space, we know a lot. So well, here in this picture, I'm just showing you the picture that implies the existence of a boundary operator bulk state map. Okay, so there is a one-to-one correspondence between bulk states in the global coordinates and local operators, local boundary operators. Okay, so this is just a Weyl transformation. On the left, I have the usual Poincare coordinates, and on the right, I have the usual global coordinates of cylinder picture of ADS, and you can use a local operator inserted at the boundary point B to create a state on this constant time slice, which I can color for you if you want this constant time slice. Okay, and using that, so we know that bulk operators have an expansion in boundary operators, which is convergent, and we also know that boundary operators have a convergent operator product expansion. So that's enough basically to have all the CFT axioms. So if you put any quantum field theory in ADS, you immediately get a subset of the observables. So the just correlation functions of these boundary operators, they obey the CFT axioms. More precisely, they obey the unitarity and OPE convergence and dissociativity. Of course, if you want to have a fully local conformal field theory, you need a stress tensor, and for that you need gravity in the bulk. Okay? But this is really a simple add-on to the structure. Just putting quantum field theory in ADS already gives you most of the structure about conformal field theory. Then having the stress tensor or not, it's kind of a simple generalization. If you have gravity, you have this special operator that is conserved and it obeys some more identities. So, I mean, the story told like this in ADS really suggests that once you understand properly quantum field theory in a given background, then adding gravity should not be too complicated. Of course, this is probably misleading, as you've been discussing, like in the Sitter in particular, things should be much more complicated. But I think at least it's worth trying to understand first very clearly what is the non-perturbative setup, the non-perturbative definition for a quantum field theory, and then add gravity perturbatively and see what new features arise. Okay, so let's see in flat space what is the status of the problem. It's not as good. So in flat space, of course, we have local observables like in quantum field theory in ADS, but again, we can focus on the subset of observables defined at infinity, which are the scattering amplitudes. And here we have a list of properties that we expect from them, but really these are not on a very solid footing. So, for example, well, causality we like, but the actual mathematical formulation in terms of analyticity, we have only partial proofs of some analytic behavior of scattering amplitudes. We don't have a full understanding of what is the analytic structure of scattering amplitudes non-perturbatively. And so here we also have a guess of what happens if you add the graviton, right? Okay, we have a new more particle, a massless particle that has to obey some specific soft theorems, so some relation between different scattering amplitudes. At least in total space-time dimension greater than 4, right? In 4 dimensions, we don't even know how to define finite infrared finite scattering amplitudes, or more precisely, we know how to define some infrared finite observables, but these infrared finite observables, we don't know the list of properties that they should obey. Okay, so I think this is also a very important open question. is if you have a good guess, whatever, Faddeev Coolidge or some hard celestial amplitude for what the infrared finite amplitude in a four-dimensional gravitational theory is, then the important point to understand is what are the actual properties? How does unitarity apply for this amplitude? How does analyticity apply for this new observable? I think this is, as far as I know, very much an open question. And now here I want to connect with what Eliot was saying. I think here there is still a lot to understand, in the sense that in principle you can start from the ADS case where we really know the axioms. I think we know really for quantum field theory and ADS everything non-perturbatively, and from those axioms try to take the flat space limit and see what we get for the scattering amplitude. And this, I mean, we have several formulas that work in many cases, but I don't think we have, I mean, in particular, there is no derivation of analyticity starting from ADS. It's a bit worse than that. So there are examples. So we've done several examples where we use the conformal bootstrap. So we run the numerical conformal bootstrap, and then we extrapolate to the flat space limit, essentially by taking the limit of large dimensions. Because if you want finite masses, as Eliot just said, the dimensions are masses times the radius of ADS, so dimensions become very large, conformal dimensions. So you can analyze that and take the limit, and sometimes, most of the times that we did it, we can match those results precisely with bounds that you get from S matrix bootstrap. So there's like a beautiful flat space limit working at the level of conformal bootstrap goes to S matrix bootstrap in actual numerical computations. But there are examples that we've done where it doesn't work. And we do not fully understand why it doesn't work. Okay? Usually these examples involve particles of different mass, whose mass ratio is relatively large. Like, so in the example I have in mind, if you want, I can explain. You have two particles. One is 1.6 or more than 1.5 times heavier than the light particle. And then when you do scattering of particle 1 with particle 2, there are bounds on cubic couplings between these particles that don't match between what we get from the S matrix and what we get from conformal bootstrap. Okay, so there is something to understand about the working of this limit. Okay, and finally, just about the sitter. So here I think the status is really poor, even at the level of quantum field theory. I mean, we know a lot about perturbative quantum field theory. So there's been a lot of work in computing diagrams in ADS for cosmological correlators. But at a more non-perturbative level of what is the best structure to define quantum field theory, I think we don't know enough. So for example, one can write exactly the same type of formulas that I wrote for ADS, but now expanding close to the late time boundary. And so we can also define boundary operators by the late time expansion of bulk fields in quantum field theory. And then these boundary operators should also have some kind of OPE. But there is no state operator map that we can use to ensure convergence of this OPE. And so this is really an open question. We don't know. So unitarity, we know partially. So for example, here I give you an example. If you take a 4-point function of boundary operators, you can obtain a unitary relation by, if you insert here the resolution of the identity in terms of the Hilbert space. And since the Hilbert space has to decompose into reducible representations of the de Sitter isometry group, you know that you will get some principal series and possibly some extra representations complementary or discrete. And again, in practice, we know that principal series always appear. It's kind of generic in quantum field theory examples. But complementary and discrete, this example by example, so for example, complementary, in principle, it can be continuous, right? You have a continuous range of labels that allow complementary series. But in concrete examples, you always see discrete particles. So I like the analogy that the complementary series in the sitter is like the single particle states in flat space. So they come with some isolated value for mass square, while two particle states create a continuum of. So I like that analogy, and I think in examples that's what we observe. So this is also an important thing to understand, not just like what's possible from group theoretical point of view, but what's actually realized in a good quantum field theory, in some generic quantum field theory. And I think this is also not fully understood. And okay, this is also a complete, mostly open question. There is some work perturbatively. So from the sitter, you can, from perturbative diagrams in the sitter, you can extract perturbative S matrix elements by focusing in some specific residue. So it would be very interesting to understand how that works more generically, non-perturbatively. And then I won't even speculate about dynamical gravity. I would like to see what fails if you just add perturbative gravity, and you will have a new operator, and you will see. Of course, this is really completely different from the expectation that the sitter should have finite entropy. So it should be some finite dimensional Hilbert space, which is very far from this perspective if you just use quantum field theory. Okay, this is all I wanted to say about the more simpler problem of just quantum field theory in this maximally symmetric spacetimes. Thank you.
Thanks, João. There's a question for you in the chat. I think maybe we go to Loga and then we cover all the questions that are in the chat. So if you have any questions, you can write them in the chat at any time.
Hello.
Hey.
So, yeah, let me share the screen just a minute. Can you guys see my share screen?
Yep.
Yeah. Okay. Hi everyone, and I'm happy to join all of you in this very interesting workshop. And I should thank the organizers for putting together this workshop. I think I learned many things, especially because it's a it's a set of people who don't talk to each other usually. I also thank the organizers for giving me the opportunity to present my viewpoints. So I will just say a few things. Hopefully it'll be done in some 10-15 minutes. Okay. So just to kind of motivate where I'm going and what's the kind of viewpoint I want to kind of present in front of you for the next few minutes. So I just want to point out something, which is that somehow when you go out of ADS, when you think about de Sitter and flat space to some extent, somehow the real-time non-equilibrium perspective seems essential. Somehow the kind of non-perturbative states we are thinking about and are all kind of very non-equilibrium. Just to kind of give you an example, the flat space Schwarzschild black hole is not an equilibrium state, it has a negative specific heat and so on. It's not an equilibrium state unlike large black holes in ADS, or the kind of, black holes people count the entropies of the extremal black holes. So these are kind of, very far from equilibrium states. And with de Sitter, things is in some sense even worse, because you cannot even define a global equilibrium. because there's no global time-like vector to define an equilibrium. So there's something very, quintessentially non-equilibrium about these things. Okay. And also, like another way to say this is that the natural boundary conditions in flat B-Sitter are open boundary conditions. We had some discussions in previous talks in last few days about leaky boundary conditions, for example. Like sometimes in EDS also, like like in this page of discussions, we want to put leaky boundary conditions. So the point is that like somehow like I feel that many of the questions that we are kind of entangled with and we kind of fight and struggle with eventually boil down, whether it is in any lambda, with some kind of non-equilibrium questions, because these are hard questions, even in systems that we understand very well, even in free theories, like non-equilibrium is a very challenging question. And hence it's not a surprising statement that we kind of struggle with it. And I feel that, this is something is kind of our next frontier. So what, like with that kind of like a broad, prologue, I just want to kind of make some remarks on how to think about such quintessentially non-equilibrium open systems, okay, within field theory and more specifically within gravity and so on, okay. There are, within gravity, there are many things that we only are beginning to understand. But the main thing, I think, which those of you who have thought about non-equilibrium things in one context or another is know that, you can't describe it with a single copy quantum field theory, the textbook quantum field theory that you learned from Peskin and Schroeder or whatever textbook you had in your first quantum field theory course. But it requires something called the Schwinger-Keldysh formalism, which doubles the degrees of freedom and kind of thinks about it. So I will kind of my aim here is to kind of give you a bird's eye view of recent advances in real-time ADS holography. How do we think about these kind of Schwinger-Keldysh in asymptotically ADS spacetimes, and what have we learned in last year or two, okay, especially. And what do these advances tell us about B-Sitter, about which we are just beginning to think about. I don't have anything much to say about lambda equal to 0, except perhaps as a limit of these two situations. But that's perhaps okay, because I think many other people who are more competent than I have talked a lot about flat space already. Okay, so just this is like a crash course on Schwinger-Keldysh, so this is what you should do if you have a general density matrix, and if you want to think about calculating correlation functions, in a general initial density matrix. So what you do is you kind of take two copies, okay, a Bra copy and a Ket copy of every field that you have. Okay, let's say you have a scalar field. Then you think about the right copy and the left copy, and if it is a unitary quantum field theory, you kind of take an action for the double fields, which is kind of decoupled, where which is S of phi r minus S of phi r. Then S of phi r is just a statement that the right copy basically evolves like ordinary field theories, you're just path integrating over the Ket copy like you do the usual Feynman path integrals. In the left copy, you put an additional minus sign. What the minus sign does is that it kind of, evolves it with, a time reverse boundary condition, so to speak, which is the correct thing to do for the brass. Okay, so the idea here is to kind of evolve the density matrix rather than evolve the state as we do in Feynman path integrals. And then, the thing that you're calculating at the operator level is basically the generating function, which I've called as ZSK, where you have a trace of U rho U dagger. Okay, then you take some initial density matrix, okay, which is in general a non-equilibrium state. Okay, often it's a thermal density matrix, but it's generally a mixed state and a non-equilibrium state also. And you kind of evolve it in the right and left by U and U dagger, but you turn on different sources in the right and left, and then you take a trace. Okay, note that if you set the trace, if you take the sources equal, okay, if you take right and left equal, then by the cyclicity of trace and unitarity, this will just evaluate to 1. Okay, this path integral will evaluate to 1. So this is a way unitarity appears in this real-time kind of setups, that when you set the right equal to left, you have, then these things basically collapse. So this is what I will call a Schwinger-Keldysh collapse. And one of the things that insights that goes back to Feynman and Vernon in 1960s is that if you start with such a theory, unitary theory, and you start integrating out environmental fields, your action is no more, decoupled. Okay, so the action is decoupled here, but the boundary conditions couple the right and the left. Okay, both in the initial time and the final time. But if you integrate the environmental fields, there are couplings at the level of action also, which kind of show that the theory is non-unitary, and you're talking about an open quantum field theory that you integrated out in the environment, which you should have kept in order to preserve unitarity, and hence you have various non-unitary contributions, but of a very specific kind, of the kind such that still if JR equal to JL, the Schwinger-Keldysh collapse still holds. Okay, the technical details are not very important, because there's not a place to kind of go to the technicalities, but just to kind of roughly tell you what I'm going to be talking about. So there's this double copy, okay, which is a natural thing to evolve density matrices. Okay, so with that, very brief thing, I want to kind of ask this question of how you might want to do this path integral, this kind of a path integral, but in gravity. Okay, since we understand ADS, the lambda less than 0 case, the best, so let me just talk about the lambda less than 0 case, and especially in near equilibrium states. So at in the black brane diagrams. Okay. So it's clear that there should be some kind of doubling, okay, that the degrees of freedom should be doubled, okay. But the question is about the boundary conditions and how you kind of solve them, and how you kind of pick the saddle point, that gives you the sensible answers and so on. And I should emphasize that beyond broad statements, we still do not know answers to these questions very well. Okay, not to the extent that we understand Euclidean ADS-CFT or equilibrium ADS-CFT. Okay, we don't understand this kind of non-equilibrium question. So as a beginning, we can just start by doubling this black brane. We consider just 2 copies of this black brane. Okay, and then and then you can identify it at the future time like boundary. Okay. And this is a kind of a prescription that goes back to Skenderis and boundaries, about 10-12 years ago. They wrote a series of papers where they basically proposed that this is what you should do, which is a very sensible thing, right? You just kind of double it and try to stitch the 2 geometries together. The issue, of course, is that how do you stitch together at the horizon? Okay. So this is also a future time like boundary as far as an exterior observer goes, as far as the boundary goes. And the point is that since we are identifying the future time like boundaries, it's there's a suggestion that you should just identify. So the idea is that you just take 2 copies of the exterior of the black hole and the black brane. Okay. And then you identify them at their horizons. Okay. The question is that how do you do it? How do you identify them? It's not easy to stitch them. You have to stitch them together in a smooth way, and you should also check that the way you stitch them together. If you kind of solve equations in that double geometry, the boundary conditions give you Schwinger-Keldysh collapse and things like that. Okay, so this is not obvious. Okay, and but there's a proposal, which was made by Crosby, Glorious, and Liu, about 2-3 years ago, and by now, there's a lot of checks of this proposal. Okay, so they checked it for quadratic probes, but now me and others and my collaborators have, and other people have checked, in various kind of interacting setups, which is a very non-trivial check. So it has passed many non-trivial checks, and it kind of satisfies, the basic requirements, like the Schwinger-Keldysh collapse. Okay, that we already expect from the CFT. Okay, so many qualitatively different examples work. Okay, but it is still at the level of this thing, in the sense that we do not have any derivation of this prescription, in the sense that it's not like anybody has looked at the space of all saddle points and argued that this is a dominant saddle point, for example, something like that. That kind of an argument is still not there. But it's a solution of the Einstein equation of, it's a complex solution of the Einstein equation. It's a complex saddle, which I'll describe in a moment, very briefly, and it seems to kind of, do the job. I mean, I just want to show that there are many checks, by now, over the last 1 year, 1.5 years. Okay. So what is the idea? The idea is that, you go to you first work with, ingoing edited Finkelstein coordinates. Okay. And in that, so it's a very coordinate dependent prescription. That's another limitation of this prescription, because, it's just a proposal. Okay. But and the statement is that, you go to a constant B slice, right? A constant ingoing editing Finkelstein time. And in that time, you take the radial coordinate. So let's say you ignore every other coordinate other than R and B. Then the radial coordinate is just an interval. Okay. The exterior is just described by R equal to RH to R equal to infinity, which is this red line. And then you think of complexifying the radial coordinate. Okay. By giving it, a slightly positive imaginary part and slightly negative imaginary part, and identify it as the left and the right copy, the way I have shown it. So this diagram, you should think of it as in a complex R plane, okay, where the real line is this red line, okay. And the point here is that so what they said was that you have to take this left and the right copy, and you basically though it doesn't look smooth, you basically smoothly connect it by going around. Okay, so you have a contour with a slightly negative imaginary R, and you have a contour with a slightly positive imaginary R, and you just around the horizon you just go around. Okay, you kind of go in the complex plane, and you just go around and smoothly connect it. Okay. So the point here is that the ingoing solutions, which are analytic in B, right? They're analytic solutions in ingoing edited Finkelstein coordinates. They kind of don't have branch cut in complex R. So if you make them if you make R complex, they do not get any branch cut. Whereas the Hawking modes, which are non-analytic, they usually have a log R, which comes from the tortoise coordinate, log R minus RH kind of dependencies. Okay, which comes from the dependence on the tortoise coordinate. Okay, because they kind of they go like e to the power minus I omega u rather than e to the power I omega b. Okay, which if you write in terms of b, you get log R minus RH factors. And if you expand, you get log R minus RH, and that means that they suffer a branch cut. The Hawking modes suffer a branch cut, which means that while the up and the down contours cannot be distinguished by just infall solution by the quasi-normal modes, the Hawking modes, kind of when you go from the up contour to the down contour, okay, they kind of shift by a quasi-normal mode, basically, okay, by a very specific quasi-normal mode. And the point is that so you just take this geometry, okay, and then you kind of now tensor product this B and X, okay, with the CFT coordinates and the boundary coordinates, and then you get a geometry, and you just impose a double Dirichlet boundary condition, okay, on the non-normalizable modes at RC plus minus I epsilon. Okay, for scalar systems, the idea is that this is the prescription. Okay, so this is just given. Okay, it's not a as I said, it's not a derived thing, but the point is that if you do it, the statement is that it gives you sensible results. Okay, so that's a claim. So this is as far as the scalars. Okay. So one thing which is which was not resolved in the original prescription, which took a long time for all of us to figure out, okay, was that what do you do when you have gauge theory and gravity? Okay, the main issue here is that this kind of a double Dirichlet boundary conditions starts clashing with basically constraints on the radial slice. Okay, so basically if you just take a double copy of, for example, if you have a radial Gauss constraint, let's say think about the Maxwell theory. Okay, you can't impose a separate radial Gauss constraint at R equal to RC plus epsilon and R equal to RC minus epsilon, because if you impose the Gauss constraint on one slice, and if you impose other radial dynamical equations everywhere, okay, that automatically imposes the Gauss constraint on the other slice. So in some sense, there's only one Gauss constraint, okay, radial Gauss constraint, okay, which is basically the grad mu f mu r, of the Maxwell equations. the up R component of the Maxwell equations can be imposed, only once. Okay, so which kind of, it goes against this double copying thing. Okay, and it's not clear how do you deal with it. Okay, and a similar issue appears with, of course, gravity, because it also has constraints. Okay, so whenever you think about gauge theoretical systems, okay, so this prescription has to be rethought. Okay, so this is one lesson that when you start thinking about real-time analysis, okay, you kind of get into new kind of questions which you don't think so much about when you think about Euclidean calculations, right? In Euclidean calculation, what would be the corresponding Euclidean calculation? It would be a cigar geometry, okay, and there will be just a single boundary condition, right? You just do a Euclidean black hole, which is a cigar, and there's a single boundary condition. So this is an issue which appears, when you think about gauge gravity in real time, only when you start thinking about it in real time. Okay, so the new kind of issues appear when you start thinking about real time, which don't appear, which are not obvious, and which are not apparent when you think about it from the Euclidean point of view. Okay, and so that's one lesson. If nothing else, I think they should take home. And the point is that so there are many issues. With gauge gravity, only one issue is this: there's a Gauss constraint problem, which are all kind of related in some very intricate way, which I'm not sure we completely understand. So one of the other things is that, of course, that there are very long-lived modes, which is in this problem. When you have a gauge theory, we know that there's a diffusion mode in the boundary theory, in the boundary hydrodynamic. There's a boundary hydrodynamic modes, and if you kind of integrate them out, in general, you get something which is not a very derivative expandable solution. Okay, you might not care so much about it, but if you kind of want to solve it systematically and want to understand how related to hydrodynamics, then you want to kind of freeze this hydrodynamic modes and get them sensible. Okay, so that's the point, that we want to kind of separate the long-lived modes to short-lived modes, which is another kind of a very essentially real-time question. Okay, because in the Euclidean time everything just dies. Okay, I mean, there's nothing long-time, short-time, but the distinction between long-time, short-time appears in the real-time modes. Okay, and then there's some technical thing about how you should solve it, which is about radial gauge, which is also very, very commonly used gauge, which is not very good. If you want to understand Hawking radiation and so on. Okay, but let's ignore it. But the point is that many of these issues can be tackled. Okay, this is what we found. Okay, in anti-de-Sitter, if you kind of separate out the modes carefully, in this scalar vector tensor harmonic decomposition that many people are probably familiar with, solving linear Einstein equations, and what we do is we freeze non-nominal modes, which is the standard thing to do in gravity tensor sector and the gauge vector sector. Okay, which correspond to the short-lived modes. But in other sectors, the correct thing to do is to freeze the normalizable modes instead. Okay, which is something that we are not, we are said we should not do, in standard AD safety reviews and so on. Okay, but that's the correct thing to do here if you want to freeze the hydrodynamic modes and only integrate out the ultraviolet degrees of freedom of the conformal field theory. And this can be actually used, I mean, let me not go into the details, but this can be actually used to derive a Wilsonian influence functional, which just integrates out the short-lived modes and keeps the hydrodynamic mode frozen. So it gives an influence functional in terms of the hydrodynamic modes, which are basically the effective Schwinger-Keldysh action for the hydrodynamic modes, which has this coupling between the right and the left copies and so on and so forth, which kind of passes various tests. Okay. So let me kind of basically conclude here, but because this is the basic idea that I wanted to say about the anti-de-Sitter, and I just want to say a few words about de-Sitter, okay, and other signs of lambda, since that's what we are all interested in, in this conference. So what about other signs of lambda? Okay, there are various very quintessentially real-time questions which appears in other signs of lambda. Okay, one thing which I want to flag here is something that many people here in the audience probably are aware of, which is another way of thinking about de-Sitter holography. Okay, which is not talked about so much, in this conference also, which is that, which is not to think about it from the early time, inflationary correlators or very late time correlation functions, but to think about in terms of an observer, okay, in terms of an observer and its static patch, and what the observer observes, and try to write down some effective theory for this observer, okay. And the point is that this observer, feels radiation reaction, okay, and which kind of, dissipates the energy of the observer, because the observer is, let's say the observer is a charge, then if the charge moves, of course, it radiates and loses energy, right? It seems a radiation reaction. It sees a damping, okay, this Abraham-Lorentz damping kind of force, okay. So the point is that, so that provides a kind of a dissipation, like in the case of hydrodynamics, you have a viscous dissipation, and whereas, in the case of de Sitter, there's a cosmic background radiation which comes from de Sitter, okay, which comes with the Bose-Einstein factors, the de Sitter temperature, and so on and so forth, okay, which provide the fluctuations, okay, that this observer sees. And you can kind of talk about the influence phase of this observer, which is a quintessentially real-time quantity, okay, and you can ask, can you compute this this quantity, by the kind of trick that we use, where you kind of double the gravitational setup, where you kind of double the static patch and then stitch together at the de Sitter horizon, and that basically works. Okay, I mean, that's what we checked. But though there is a lot of things which we still don't understand, which are about boundary conditions and counter terms and so on and so forth, which, as I said, are kind of slightly different in real time, and sometimes can be quite different in real time than in Euclidean kind of correlation functions. Okay, so one can ask, whether one can do similar constructions like this for for an observer in black hole interior and so on. Okay, so let me just this is my last slide. Okay, let me just in the spirit of this conference, let me just kind of wrap up and say what are the things that I think this kind of an exercise, thinking about things in real time, like on real time holography, what are the lessons that it is trying to teach us. This is, of course, I mean, some of it is speculative and this thing, but I think so one is that there is this there's a novel saddle points, okay, in real time holography, which are kind of which kind of seem to have lead to completely new questions about boundary condition, gauge invariance, about the analog of holographic renormalization and so on and so forth, okay, which we do not see in the Euclidean picture at all, okay. So that's something that I want to emphasize. So which means that there are things that there's something to kind of think about in the in the real time holography in the real time, okay, rather than as an afterthought, okay, to Euclidean questions, where we always many people have this kind of attitude that they solve the Euclidean problem and analytically continue, right? Which is a very which works a lot of times, which is what standard quantum field theory books teach us, which works for S matrix, for example, for QFT in flat space. But the point is that somehow many of these holography and gravitational questions, the way these things work, seem to say that we should kind of take the real time seriously, and it might be even needed to define the observers. For example, the observables that the observer sees, which is the radiation reaction that an observer sees, I think is a quintessentially real time question, and there's no simple Euclidean version of that, I think. Okay, and yeah, I'd like to just say it's my viewpoint, but maybe people here might disagree that many of the issues that we are talking about, like unitarity, causality, and so on, okay, I think should really be formulated in terms of Shinga-Kellysh real-time holography and in open systems, for us to kind of really understand what is happening in real time, rather than rather than understanding them in an abstract level at the Euclidean level, from the Euclidean side. Okay, so let me just stop there and thank and thank you for your patience. Yeah, so if you have any questions, I will be happy to answer as well. Okay.
Thanks, Loga. Thanks also again to the organizers Really want to take the opportunity to say that this has been great. I'm very motivated after this week to understand all these things that I didn't know about, actually, about especially flat space, which is the one I know the least about. But I want to say now that because this is a discussion, we should open it up. So I already see 2 questions. So I think let's start with Kostas.
Yeah, hi. I just have a question for Loga for this last talk. So usually the behavior close to the horizon should be determined by requiring regularity in the interior. So why this is, I mean, why did you have to use a different prescription than just regularity in the interior?
The regularity in the interior in what sense? I mean,
well, I mean, you start from the circular Celtic contour, then you construct the extended space-time that contains that corresponds to the contour, and then you impose regularity in the interior. I mean, we did examples, including ones with black holes and horizons, and then regularity in the interior gave, and so what everybody is using, this incoming boundary conditions, the horizon. But this was something that you derive, it's not something you input.
Yeah, but we don't want the incoming boundary condition because there's Hawking radiation, right? But that basically kills the Hawking radiation. How do you get the Hawking quanta? If you put incoming boundary condition, that just gets
No, I don't want to input anything. I just want to put boundary conditions, the string Celtic, and then require regularity in the interior. That should determine the behavior.
But eventually, in your final answer, you don't want incoming boundary conditions, right? Because in the final answer, you want Hawking radiation to be present.
Well, the answer would be whatever it is. I don't want to input what happens.
Yeah, but if you don't have Hawking radiation, then it's a wrong answer, right? I would say because black holes do Hawking radiate, right? I mean, so they should have Hawking radiation. I mean,
but Kostas is, I think, implying that there isn't a choice. You just get what you get.
Yes, exactly.
I mean, to be maybe a little bit mean then to Kostas, if you get the wrong answer, then that's what you get.
No, I mean, absolutely. No, but I mean, that's the point of prescriptions, right? I mean, if, the prescription is if you get the wrong answer, then, okay, there's something wrong with the prescription. Then you have to go back and see what was wrong with the prescription.
Yeah, so the question is that what is the prescription which will give you the correct Hawking radiation? And
I would claim the prescription in all cases is regularity in the interior. You use boundary because that's, no other prescription is holographic. Holography means you determine everything from the boundary. So you give the boundary conditions at infinity, and then you impose regularity in the interior. Then that determines completely the problem.
Yeah, but Kostas, like if I don't get an answer which obeys like things like KMS conditions and so on, okay?
No, but the KMS conditions do come out when you have for eternal black holes. Okay, that we've done in 2008. You get KMS conditions from regularity in the interior.
No, not Shunya Keldysh KMS condition, not the thermophile double KMS conditions. They're different, right? Thermophile double has a e to the minus beta by 2, KMS with e to the minus beta by 2 things, right? But if you want a Shunya Keldysh KMS conditions, because I want to do non-equilibrium stuff, which I can't do with thermophile double, right?
Yeah. So if it is non-equilibrium, of course, you cannot start from internal black hole. You have to start with something which is not. Okay, you get something different. But I would claim if you use the right contour and then impose regularity in the interior, that will give you that's the answer. That's the only. I don't quite see any other possibility. I mean, in a sense, everything else. Okay, you said it's you can have a guess of how things would behave, but why making a guess where you can actually calculate and see how things should behave near the horizon?
Because I think we don't really know. Because I think I would say that we don't really know. Because we're thinking about, the space of these double geometries, right? Okay. And in general, with some Euclidean caps and so on and so forth, as you guys said, okay. And so as a general statement, I agree with what you guys say. In fact, I don't think I'm contradicting anything that you say, okay. The question is that, yeah, so it's regular. Okay, things are regular, fine. Okay, but I'm just saying that we do not know where that condition lands you in.
No, that's a
Because
computation you have to do, in a sense that this is a computation. You start from the general prescription, and then you do a computation to see what would be the behavior near the horizon. I guess my question is,
but I don't think any of us know how to do the computation. That's I think the point. I mean, yes, I think the prescription is correct. Okay, but the point is that, where does it land? Because one has to kind of do the computation over the space of all double geometries. Okay, which we don't have, and with all the Euclidean possibilities and so on and so forth. Okay, the claim is that, this is an endpoint of that prescription. Okay, but none of us have been able to do the analysis. Okay, to kind of connect that prescription to this endpoint. I agree. That I agree that the prescription is fine. Okay, indeed, we have to kind of, yeah. And at the end of the day, you should just specify the boundaries. Okay, and you should just, consider all possible geometries and somehow, pick up the dominant channel. Okay, I don't think I think I agree with, I think, other people who are involved will also agree with this statement. But the point is that, what is the dominant channel? What is the endpoint? What is the explicit dominant channel? Okay, but that leads us to kind of do the analysis over all the double geometries. Okay, the space of double geometries, which till now I think, it's fair to say that none of us know how to do.
Okay,
but,
so you say it's
but the claim is that,
you say it's a technical issue in a sense. You think you would get you to that answer, but you or others do not know how to actually do that.
Yeah, but in physics, technical issues which are unsolved might even be conceptual issues. So we do not know until we solve them. We do not know it's a technical or a concept. I mean, it's something we cannot do. So we cannot declare what it will be before we have any of us have done it, right? I mean, that's all. I mean, yeah, I agree with you. I agree with you that in principle it should be determined by just the boundary, that the basic holographic principles, ADA-CFT. Okay, I agree with everything that that you're saying. I'm just saying that, yeah, at this point we're not able to kind of implement the prescription. None of us are able to, but there's a guess for where the endpoint is, which seems to give us sensible answers. So presumably that's the answer. Okay, it would be good if somebody showed it. Yeah, if one of us really pushed it through and showed it, but it does not happen yet. Yeah, so that's all I'm saying.
Okay, no, I mean that's clear. Yeah, thank you.
Julian, go ahead.
All right, thanks. Let me unraise my. Oh no, it is. Wait, okay. Anyway, I have one comment and I have a question. So one comment was actually on your thing, Tarek. Of course, about this point of whether it's a choice or not. So I actually disagree.
That was meant to be controversial.
Yeah. Well, I disagree with it, and I disagree with it because let's just say, for example, we have our n=4 case. So if it were a choice, then your prediction is that there is some ensemble of n=4 theories that has like a large number of parameters. Let's say in the ideal case, e to the s number of parameters. So that's one part of the comment. And the second part is that I still don't think that even in the lower dimensional examples where there are very good indications for exact dualities between matrix models and, for example, JT gravity, actually any of them has been shown to work non-perturbatively. And so one might say that maybe the answer is that none of them even work non-perturbatively. So the situation is more like the higher dimensional one. So, so my comment is that I disagree that it's a choice, but in some sense, of course, we don't have all the evidence for it yet. But the alternative to it being a choice is that there just are no known examples and no knowable examples in which actually the ensemble makes any sense really non-perturbatively, completely mathematically. So maybe you want to reply to the comment, but because my question is actually to a different part, not even yours. So hold back.
Well, why don't I reply to the comment and then you can ask your question.
Yeah, I mean, you hold the power, so you decide.
Well, I mean, no, but so that it's not, so that we don't lose track, is what I mean. This is very democratic. I don't hold any power. Well, my response to the comment is that, okay, this is now we're entering the space of religion and belief, but
No, no. Then tell me how it works.
No.
For n
Wait.
equals to 4.
I was about to explain my religion and my belief.
No, just tell me how it works for n equals to 4. What's the ensemble? It's
Well,
not a religious question.
Let me just make a quick statement, and then let's see if you agree or disagree with it. But the statement that I want to make is that I don't think that we know how to ask questions precisely in gravity. And the reason that we love holography for whatever sign of lambda we choose, we like it because it allows us to make precise statements. Gravity is an emergent object that comes from integrating out a bunch of degrees of freedom. And
Sorry, but then you're saying that there isn't a dual to n equals to 4.
Yeah,
that would be the conclusion.
I'm saying that n equals to 4, there is an object that at low energies looks like the dual to n equals to 4. There is for example, take the JT gravity example. I don't think there is something called JT gravity. I think there is something called a matrix integral that gives me answers. And I think that that matrix integral looks like a gravity that is disordered, but that gravity that is disordered doesn't make sense. It's just a matrix integral. That's how I think of holography. And so there is
that won't work. That won't work for n equals to 4. At least nobody knows how this works. Not even.
Right, but n equals to 4 is a different example. It's a different choice. That would be my my perspective on that question.
So then to be a little bit conciliatory, I think that in lower dimensions there's maybe still space for your choice. Although my personal inclination is that probably we will find out that there isn't. But in higher dimensions, I don't think you have the choice. Nowadays,
well, we need to find
what we know about field theory and what we know about n equals to 4 and any kind of construction like this, we know that you don't have the choice. So, yeah. Anyway, I think Alex.
Now you can ask your question. I see Alex has his hand raised.
Yeah,
but
he's probably going to say something.
Unless your hand raising is relevant to this part of the discussion, Alex.
It is, yeah, it is.
Okay, why don't you go ahead? Sorry, Julian. Is that okay?
The comment I just want to make is, whether or not n equals to 4 has a dual. I think we all believe that n equals to 4 at the perturbative level has a dual that you can specify with, its own variables, and that answers in both cases agree with one another. Whether or not that's true at the non-perturbative level, I think, well, okay, I don't know. Maybe other people have opinions. This is maybe a question of belief, but I think there is a fundamental question in asking, do we think that string theory can produce the actual discrete spectrum of black hole microstates that you have in n equals to 4? Can it produce that spectrum in its own way with its own variables that don't basically just reduce to those of n equals to 4?
Again, you're starting to doubt the original conjecture.
Yes, but I think we don't know the answer to that question, right? Like we don't know even as a priori question whether that's. I mean, nobody can compute the spectrum of n equals to 4, but that's not. I'd say that's less of a conceptual problem. Maybe one day we'll have either the bootstrap or a computer that's powerful enough from the lattice. I don't know. There's a spectrum in n equals to 4 that will be computable one day, but we don't know if string theory can compute that microscopic spectrum.
The CFT conjecture.
Also, what about the integrability? All of the integrability results.
But that's for the planar theory, right? Like we don't think
non-perturbative. You mean non-perturbative in n, not in Taft coupling.
Yeah. I mean non-perturbative in n. Yes, absolutely. Yeah. I mean about resolving the spectrum of black hole microstates that have dimension n squared, and presumably for some value of lambda, there's a list of numbers there. And the question is whether string theory can produce that list of numbers on its own, in its own independent variables. And okay, I don't know. This is definitely the territory of religion and belief.
Very careful.
But I think the most conservative statement is that n equals to 4 provides the non-perturbative completion of what we mean by string theory.
But then why did you bring up the first part of your comment? I mean, you seem to be contradicting the first part of your comment now.
No, why?
I thought you said that it may not be possible to reproduce the full structure
Yeah.
non-perturbatively.
Yes, so what we mean by non-perturbative gravity has to be defined through the CFT, and there may be no other way. Again, I'm not claiming this is a statement. This statement is true. I'm saying this is a possibility that we have to at least consider.
Right.
I have a question for Tarek and for Logan.
Well,
but then
wait, I
also
promised
have a
Julian that he
question
would
for
get to
Logan.
his second
So
half.
we
I have a question for Logan, yeah.
Oh, we're still talking about okay.
Wait,
No,
no, wait,
wait,
no,
wait.
wait. Julian had a second part that I postponed, so you can ask your question after.
Yeah, but sorry, I mean, I don't know, maybe this is just my personal thing, but I really do want to insist again, this is not a religious question, and why don't you just construct the ensemble of n=4 theories that you propose to be dual? So that's a concrete challenge, which is not, about turning water to wine. But let me ask my other question, which also I believe is more technical. Logan, can you clarify? You said that somehow in flat space and as well as in de Sitter space, you think that open boundary conditions are sort of the most natural ones. I was not entirely sure why you said that. Could you maybe clarify that a little bit?
Because things radiate out and the radiation just escapes, right?
But we don't usually call that open boundary conditions.
It is for the let us say I'm thinking of the kind of thing that I was talking about at the end, right? Like just a single observer, okay, who is in the space, okay, from the point of view of the quantum mechanics of the world line of that observer, okay. In that sense, it is an open boundary condition for. I mean, you don't expect a unitary effective quantum mechanics on the world line because there's a radiation reaction, and things just escape in de Sitter and in flat space. In ADS, probably it doesn't, okay, but it's not clear. But yeah,
wait,
but
I mean, the fact that things can radiate to infinity in flat space, for example, does not lead to a non-unitary S matrix. And typically, this is what we call unitary versus non-unitary. So maybe that gives a little bit more of why I'm asking a context.
Yeah, it doesn't lead to a non-unitary S matrix, but like in many like real-time questions, like the question I was asking, which is if you think about the world line theory, okay, it does give rise to kind of non-unitarities in there, that's all. I mean, and you might want to think about such questions. Of course, see, I'm not saying that if you want to always think about only S matrix, and if you are very like adamant about it, you don't have to do any real-time question. You can do Euclidean questions and analytically continue. Okay, I'm just pointing out that there are other questions and there are other things. And sometimes in de Sitter, you can't define an S matrix. Then what are you going to do?
Yeah, sure. I think I understand a bit better what you meant now. Yeah, I sort of had processed that you meant something more like there is really the system should be coupled to an environment, and then you get like a non-unitary S matrix. But I understand now what you mean. Thanks.
I mean, for de Sitter, I don't think you have to be open. The radiation could be absorbed at future infinity.
I think
you can. Yeah, but I always find putting boundary conditions in future to be a bit, it's a slightly strange thing to do from a non-equilibrium point of view. But I guess at some level it's a question of taste, I suppose. But I think there are it's also a question of what questions we are asking.
Dio, you were going to say something?
Yeah, so there were two questions. One is slightly anecdotal, the other more serious. So in Logan's case, I sympathize a lot with this out of equilibrium picture, because indeed, you have your lab, you're sitting there, and things escape, and what can you do? And you sort of have to formulate things if it's eternally de Sitter, I mean. On the other hand, equilibrium physics ties interestingly into Euclidean signature, and there seems to be something about Euclidean signature in de Sitter that suggests equilibrium, even with this static picture. And I don't know what the interplay of these two things is, right? Sort of, is it again a matter of what boundary conditions you're choosing? Is it that the Euclidean picture is picking for you a very special thermal state or equilibrium state, but most of the time we shouldn't be using that.
Yeah, I understand what you're saying, but I think, like, I worry that, for example, this, like connections to equilibrium is because de Sitter is just a very maximally symmetric thing. Like, like if you go to FRW or
For the black hole, yeah. So for the black hole case, it radiates. There's a reservoir that absorbs this radiation and it shrinks, and it's very inherently out of equilibrium. For de Sitter, I can't quite see the process because the horizon surrounds you and it emits radiation and it reabsorbs the radiation. So it sort of like maintains itself somehow in a peculiar thermal equilibrium. It's not just the Euclidean picture, it's the Lorentzian picture as well, right? Where do the Hawking photons emitted by the cosmological horizon go? They go back into the cosmos. So
yeah,
okay. I can't quite wrap my head around that, of course, because, on the other hand, you emit information, there's no singularity inside the horizon, there's nothing evaporating that forces you to ask the information loss problem. I can't formulate the information loss problem for the de Sitter horizon, for example, which suggests that maybe there's nothing inconsistent with the idea that information just leaks out. So I'm very sympathetic with this open boundary game. But then there's other hints. Maybe it's just maximal symmetry of equilibrium. And the question to Tarek was, since we all emphasize the wonders of holography, one thing we haven't done, and perhaps some members in the audience of this conference may want to hear about, is imagine that there is a holography for the world, for the real world. What could you, and this is why it's a little more anecdotal, could you imagine something that we would gain insight toward the distribution of galaxies, something truly physical?
You want to live in the bulk or in the boundary?
What's that? In the world, imagine someone handed you this machine that Tarek wants for the world. What is it? The inflationary correlate that we would gain insight into? Could you give an example to someone who's never studied ADS-CFD or ensembles or anything, and be like, well, look, if we had the lotto numbers, do we really believe that this has consequences for reality, or is it a completely academic thing about quantum gravity? I can imagine inflation as a potential answer, or maybe is it the cosmological constant problem? Maybe just to engage people who didn't grow up with the ADS-CFD as the beginning and end of it all.
Well, I mean, yes, there is of course several questions that you would hope that the holographic story, the holographic machine that produces answers for our universe are. And I think, if we're going to actually be experimentalists about it, we would hope that it would reproduce our local physics. So, what is the local time evolution of, the people on this rock in outer space? So, for example, I think it would tie very much into this. It would give us answers as to, you have this paper, Dio, that was brought up by Loga about taking a solipsistic viewpoint for an observer inside, surrounded by a horizon. And the questions that you can ask in that scenario are questions that are localized to a finite strip around this world line. You can do experiments along this world line, and then you would hope to find answers at a later time. And so this machine would provide those answers for us, I think. I mean, you would, this is how we do experiments generally, right? We hit our apparatus with an object that we can control as a source, and then we wait until a later time and then try to measure it again and see how the information from that source dissipated. And those are the only experiments about our universe that we can ask currently. We can't prepare the initial state of the universe for inflation, so we can just do a measurement, but we can't probe the system. So it's not clear to me what kind of what we could gain from a machine that produces the cosmological correlators are. Maybe we would understand the early universe better, like what were the initial conditions. But you know, for our universe, I think that's the thing that we should focus on. Kostas, yeah, you have your hand raised.
Yeah, don't we want to know what happens at the initial singularity? I mean, that potentially has observable consequences. I think clearly holography would give us lessons for the real world, mostly where you try to combine quantum mechanics and general relativity. Okay, one is the very early universe, and potentially.
Just to understand, you're suggesting that somehow holography will address the problem of the initial state of cosmology.
Yes.
It will select an initial state, and that would be a very important result.
Yes. Yeah.
I agree with that. I completely agree with that. Alex?
And I imagine it would also teach us what's supposed to happen when you fall into a black hole.
Yeah.
Right? That's another question that you may want to know the answer to if you really had this machine with all infinite power and precision.
Would you come out scrambled?
Maybe.
You are shredded into pieces, I presume. I think that's without a doubt. But the question is whether or not you somehow emerge mangled, and we can make sense of that mangled you.
Yeah, I'm not sure if this is a very fair question. I mean, you could ask this question to Einstein before general relativity. I don't know.
Well, he had some things in mind, right? Perihelion of this. He was he was a little annoyed by
a posteriori check, right? It's like you check from Newton.
Maybe the answer that I would wonder about is whether it would give us a hint about the cosmological constant problem.
Yeah, but
that's possibly true as well. Yeah.
But the initial condition is not so far away. I mean, we do observe the cosmic microwave background. I mean, it's not like the perihelion is also just an experimental observation. I mean,
it was something lingering and annoying that needed to be explained. And there are a couple of like the cosmological constant problem is a little bit annoying, right? It's lingering there, making fun of us. We are stupid, you know, and maybe we have to think about it in a different way.
But I think even the CMB is confusing to me. At least, I don't know if this is a silly point, but you know, truly, you know, the way that we compute these objects. So now with Paolo maybe can discuss, or I don't know if others in the wave function world are in the audience. But you know, now what we do is we compute these observables via a wave function, and then we integrate over the wave function. But now if we include, you know, even weakly coupled gravity, we have to integrate over the metrics, you know, of this late time surface where we observe the CMB. And the question is, why is that so close to something where gravity is, you know, almost irrelevant, and we have good, well-defined observables that come from a local quantum field theory? That's a very confusing observation to me. I don't understand why that should be.
Could it just be that there's a sharply peaked saddle point in that second integral, and then
it could be, but is that a generic feature of quantum gravity?
Yeah.
Sorry, Loga had his hand raised for a while, and then I'll get to
it. I mean, I just wanted to add that, you know, like, I mean, to just Dio's question that, you know, this might not be just cosmological constant problem, though none of us are talking about it. I think, you know, like, it probably is true that we will get some constraints on particle physics also, hopefully. I mean, like, for example, is the Higgs hierarchy problem related to the cosmological
some unusual problem? Relations that we wouldn't have seen in effective field theory. Yeah, I think that would be
some kind of non-trivial consistency conditions, you know, things like what modular invariance does for you in string theory, right? You know, like, I mean, things are kind of somewhat, you know, sometimes gives you much more than what quantum field theory would give you, you know, like some deep consistency conditions, which are, I think, you know, like, yeah, holography, yeah, should, you know, if we had some kind of holographic testing, I think we could learn about such consistency conditions.
Yeah, maybe 3 generations will no longer be mysterious. Yeah.
Kostas.
Yeah, so what I want to say is that you only need to have, for the gravity question, you only need to have the gravity to be weakly coupled towards the exit of this early universe phase. You do integrate over the gravitons. It doesn't seem to me that's a big mystery.
Well, I think even if it's weakly coupled, isn't the point that you lose locality of your observables because you're integrating now over the space of 3 metrics? And yes, it's weakly coupled, but I still find it very surprising that the answer so closely mimics local quantum field theory.
Yeah.
And Paolo, you had your hand raised.
Yeah, I want to comment simply that, well, I totally agree with your confusion, but that's actually one of the reasons for which I a little bit insist on the idea that maybe we should try to, even if we get reasonable answers, to try to redefine what we compute in terms of some language where locality isn't crucial. Because maybe you can make the connection to why we get the answer that we get, and some better link to the regime where locality isn't there.
Yeah. Actually, this brings me to a point maybe that links to what João and Eliot were talking about. So, if we had this machine that for the real world, as Dio so nicely put, do you think that this would give us good IR finite observables for flat space, for example, for massless scattering amplitudes? Say if we could get this from ADS in a well-defined way.
I mean, I think it's just a fact that the scattering amplitudes diverge, right? That if you try to count the number of gravitons in the final state, it's infinity.
Well, so let me rephrase. A good IR finite, the right IR finite quantity, not necessarily the amplitude.
Yeah,
but
that I think so. When you go to ADS, it's a specific IR regulator, and by carefully taking the R to infinity limit, you could separate the things that diverge with R and the finite part. That I think it's.
I mean, if the asymptotic phase space is a Fock space, you're always going to have IR divergences, right? So you have to. I mean, the S matrix defined with an asymptotic Fock space will have IR divergences. So you have to dress your state so that instead of a Fock space, you have some other more complicated space, right?
Well, I mean, beyond the Fock space picture, there's a fact that the scattering amplitudes for massless particles. This isn't a problem that arises for massive particles. The massless particles.
No, but this is all just because you think of these massless particles as being part of a Fock space, right? Yeah, well, I mean, if you fix this, if you dress your asymptotic phase space, and you, instead of having some single massive particle, you dress it with photons, then these dress states give rise to IR finite.
It seems like that is not a unique choice. Usually in flat space, we have more than one way of dressing the object to get a finite quantity. And the question that I was posing, to rephrase it a little bit, is what is the right one? Is there a right one? And do you see that from the limit from ADS, say? I see 2 hands raised. I didn't catch who raised first.
Loga was first.
Okay, go ahead, Loga.
Yeah, so I mean, just to kind of continue the things that we're discussing, I had a question too, like both João and Eliot, so regarding these flat space limits and so on. Now, of course, the flat space gravity, as we know, has this non-renormalizability problem at a perturbated level. There's a Gorovsognaty, like counter term divergence that appears at 2 loops, and then like it has to be like it makes the theory non-renormalizable, right? Okay. I wanted to know, like, is there a understanding of how this appears if you kind of think about it as coming from ADS and from a conformal field theory, is there some statement about large and bootstrap that that there's some ambiguity which appears at some appropriate step in the calculation? Like, how do I think about it from let's say bootstrap conformal field theory perspective? Like, is it known? Is it understood?
So I think you are referring to when you have some loop diagram that diverges in flat space, right? That you need some contact term.
Yes, yeah.
UV divergence in flat space. So
yes.
So this, I mean, of course, if you just do the Witten diagram in ADS, you will see the same UV divergence. But I think you're asking how to see that in the CFT, right? In dual CFT.
Yes, yeah. So somehow this, sorry, just 1 minute. Somehow this tells me that that if you know the 3-point functions of like say stress tensor or something, like in 4-point functions there's some particular ambiguity which appears at some step. That it doesn't completely determine it, and there are actually there's actually a sequence. If you believe in non-denominability fully, there's like an infinite number of ambiguities, right? In the TT correlation function, so to speak, right? It does not, but is it understood how we think about it?
Yeah. So I think the example that was worked out in more detail, more explicitly, is just phi to the 4th, but across dimensions. So if you go above 4 dimensions, you will have this UV divergences even at one loop. And I think, yeah, this was some work by Aldai and collaborators, where they compute the anomalous dimensions of double trace operators from this one loop diagram, and they use this large spin conformal bootstrap to go to one loop order. And essentially what they see is that they get some sums that are divergent. And so you can just, what do I mean? You can regulate these sums, and it's kind of zeta function type regularization. It appears in a way, yeah, technically it appears like that from the CFT bootstrap point of view.
But the gravity part of it is not done, is that right? Just the
no, I think no one did really, because CFT with stress tensor 4-point function is a complicated beast to go to do loops with that. Yeah, nobody did this. Yeah.
But João, in a top-down model, that function is just has to be some well-defined function. Is it clear that this zeta function regularization gives the right answer, or?
I mean, in practice it works the same way. Sorry, maybe zeta function. I'm saying it. I mean, there's a freedom. You have some infinite sum. So let's say, what do I say? And the dependence on the parameters, there's a divergence that doesn't depend on the parameters. So you can absorb this divergence just in subtracting a single constant. So it really is the same number of parameters as the counter terms you would have in field theory by subtracting this UV divergence. So it's not like you introduce a function of freedom, you introduce exactly the same number of parameters that you have to do in the usual QFT normalization.
But what fixes that actual number in n equals to 4, say? Like, there's no free numbers in a 4-point function, even on one loop in n equals to 4, right? It is what it is.
Yeah, but I mean, that's...
So is the number non-perturbatively fixed, or?
Right, you could ask the same question. I mean, take the string theory scattering amplitude of gravitons in 10D, say. So this is some finite, right? Some amplitude that comes from string theory. You can get order by order in G string, and now you can try to compare that with what you get from effective field theory by doing loops in supergravity, and to match that, whenever you start getting UV divergence supergravity, you have to have specific counter terms that match the number. So it's true. String theory will predict for you the precise values of the higher dimensional operator.
So you're saying it's lambda dependent, essentially, that value of the number in n equals to 4, for example, would be lambda dependent.
I mean, there are examples where we can actually match it. I think some of the group of kind of James Drummond did also similar stuff that João described, and then they can see it explicitly. You can compare, let's say, the R square. You know, the R square has a specific coefficient in string theory, and then you can also see that the bootstrap fixes the coefficients in an equivalent way with what you would get from string theory. It hasn't been done for all of them, but they have seen it in some cases. So the CFT would give this counter terms with specific coefficients like string theory does.
I see.
Pablo, you lowered your hand. Was that on purpose?
Yeah, it was on purpose because what I want to say is that became a little bit old because it was related to your IR divergence comment for the amplitude for massless states. No, I just want to say, I mean, we do know that we are working with the wrong asymptotic states when we talk about the S matrix for massless particles, and then you see it when you, rather than using momentum eigenstates, you use eigenstates of the Casimir of the Lorentz group, where if you take the translation generator, it takes you out from the Hilbert space. But people never worried about it too much because the actual IR finite object is the cross-section, and we know that the IR divergences has to have the precise structure that in the cross-section things are gonna cancel. And for that reason, people never ask in the scattering amplitude community never worried about let's try to have a well-defined object, except this work by Faddeev-Kulish. Now, it will be nice to do it, to have it if it's possible, but at least, especially from people worrying about phenomenology, for them is not one of the most pressing questions.
Well, yeah, also because you can do this inclusive amplitude type IR regulation. Kostas, you had your hand raised and then you lowered it. You're muted, I think.
No, I think I already made the comment. So that's why I lowered down. Yeah.
All right. Yeah. Okay. So there are no hands raised. I can ask one further question myself. So, yeah, my question is for Loga. So you showed this picture in your slide about, in the Euclidean, taking this contour, this blue contour that skirts the branch cut, goes above it and below it. And yeah, I was wondering if you do that. So, when we think about equilibrium for the black hole, this is a very bizarre thing when discussing quantum field theory, like for example, thermal quantum field theory, we think of the cylinder and we don't think of the cigar. Euclidean gravity somehow tells us to compute things in the cigar, but somehow we're supposed to compute in the cylinder. So yeah, I was wondering if, imagine now unwrapping your blue contour, would that somehow give us back answers on the cylinder, or is it, somehow it's a different question where we've, as a single Euclidean geometry, it might be something completely different. Well, I was wondering if you had some thoughts about that.
I think the geometry I was describing, you should think of it as some real-time version of the cigar, so to speak.
Like
some Schwinger-Keldysh version of the cigar, some doubled version of the cigar. I mean, it's just in the sense that.
But it skirts. Yeah. It doesn't. Does it cap off in the same way?
Well, it doesn't cap off in the same way, but
yeah.
But the answers are the same. So I guess, okay, let me put it this way, that if you kind of reduce this to the equilibrium situation, okay, if you just calculate like some equal time correlation functions, I think, your calculations will probably reduced to the cigar in some sense. But this not being understood very precisely. It's, but I think like the claim is that this geometry is the analog of the cigar. I mean, and generally like all the geometries because in some sense like how do you obtain the cigar? You kind of start with the circle and you say what is the dominant saddle, which kind of closes it. So while we have not shown that this is the dominant saddle, but I think the basic argument by Skenders and Madris is that you just do the same thing called Schwinger-Keldysh contour, right? Like you just take the Schwinger-Keldysh contour of the boundary theory and you just ask what is the geometry which asymptotes to that, and the kind of conjecture is that this is the dominant saddle that dominates that kind of a prescription. Does that so in that sense it's a very analogous to cigar. That's what I mean.
I see. No, now I understand. No, because I don't know if you saw Daniel's session a few days ago, but there is this confusion. Yeah, there is this confusion as to why we compute things in the cigar, right? I mean, when you think of quantum field theory on some background, you don't let that circle contract. But somehow when you have quantum gravity, the correct thing to do is to compute in the cigar. And yeah, I think this is an important point that.
Yeah, I think this saddle probably inherits all these kind of puzzles that like Daniel was talking about. Like there might even be some, though nobody has really studied it, there might even be some funny relations that you kind of superpose some things and you end up with the same answer as the geometry, things like that. But yeah, so but I won't be surprised if something like that happens. Like the things that happen with the cigar happen with here also. Yeah, I think this just inherits all these puzzles with additional real time just put in.
Yeah, I see. Any further questions? We're 3 minutes away from my IR cutoff. But if there are no further questions, we could thank everybody for this wonderful workshop and thank each other.
Thank you. Enjoy your dinner.
Thank you. Thank you.
Yeah, I'd like to also thank all the speakers and all the participants for making this into a really lively workshop. And also thank my other core organizers, Gizem, Joris, Gideon, and Ondra, for all their efforts in making this as smooth as possible. And also, thank all the participants for making the event possible.
Yeah, thank you. Yeah, this was amazing. Great fun.
Bye, everyone.
Yeah, bye.
All right, I will go myself. Thanks, everybody. Take care.
Thanks
everyone.
Thanks.
Bye.
Thank you. Bye.